The recording. Hey everybody, we're live and in stereo. I've started the recording in two places, one on Zoom and one in the app. The app recording would be available on your portal, and the Zoom recording would probably be also be uploaded onto YouTube. The app recording is going to be much more crisp, and it's going to be in 1080p, so you guys can see that later on your portals. But yes, the only thing is that you won't be able to see the face in my app, and now you guys can see me. I'm live and in stereo. So I hope you guys are all ready to just demolish these past paper questions, okay? These are all the questions for chapter number 1 that has been tested till date. They contain all questions from all variants, and I've compiled every single question on my own. So just realize it's very easy. You will see, as long as you've taken the classes and you've jot down important points. That's it. That's all I require. ठीक है जी? Chalo, without further ado, let's start. It's saying question 1 says, I'm going to go a little quick on this, and whenever you guys have any question, just raise your hand and ask me. But please don't ask me questions if you haven't watched the relevant class recording. Okay? Now, question 1 says, cobalt, rhodium, and iridium are metals in the same group of the periodic table. The shorthand electronic configuration of cobalt is argon 3d7 4s2. We need to understand that the 4s subshell is filled first before the 3d, because the 4s is at a lower energy level than the 3d. And is cobalt argon 3d7 4s2? Let's check it out. The periodic table is right here. Let's use the periodic table to our advantage, huh? So let's use this. We need to check out cobalt. Cobalt is right here, right here. So it is in fact argon, and then it's 4s2, 3d1, 2, 3, 4, 5, 6, 7. So argon, 4s2, 3d7. But you write the 3d first, because Cambridge tends to club the, all the subshells based on principal quantum number. So it clubs the 3s, the 3p, and the 3d together. That's why you could see 3d before the 4s, but realize that the 4s is filled first. Now, identify what is meant by argon by giving its full electronic configuration. What's the full electronic configuration of argon? Argon is right here. So what's the electronic configuration? It's 1s2, 2s2, 2p6, 3s2, and 3p6. That's it. Argon has 18 electrons, right? So 1s2, 2s2, 2p6, 3s2, and then 3p6. That's it. 1 mark right here. The lowest energy electrons in cobalt are in the 1s orbital. Draw the shape of the 1s orbital. You're not required to draw a 3D diagram for it. So how would the 1s orbital look in 2D? It would just look like a circle. You don't have to draw the x-axis, the y-axis, the z-axis. Just draw the shape. That's a circle. Boom, another mark. Deduce the number of unpaired electrons in a cobalt atom. Now, if you were to check out the cobalt atom, for this you need to write down the electron inbox diagram for yourself. I call it the EB diagram. So you have to complete it. Now, what's the electronic configuration of cobalt? It's argon 3d7 4s2. It's argon 3d7 4s2. Now I have to check out how many unpaired electrons are there, and for that I'll have to write down the orbital electronic configuration. So that's the 4s, and that's 4s2. The d subshell has 5 d orbitals, and let's start filling it out. So 1, 2, 3, 4, 5, but it's 3d7. So it's 5, and then you start pairing it up. 6, 7. How many unpaired electrons are there in cobalt atom? 1, 2, 3. That's 3. Boom shakalaka, done. Other mark, done and dusted. Next question. Table 1.1 gives some details about stable and naturally occurring isotopes of rhodium and iridium. Number of protons. What are the number of protons? That's 45. That's 77. The smaller number is obviously the number of protons, because realize that the mass number also takes into account the number of neutrons, right? So even if it was written even if it was written flipped like this, never get confused, because the smaller number is the proton number. Obviously, this is the conventional way of writing it, but the smaller number is always the proton number, because the mass number is the total number of protons and neutrons in the nucleus of the atom. So it also takes into account the number of neutrons. Yes? So that's 47, and iridium, that's 77. Good stuff. Now, how many neutrons are there? 103 minus 45. He's already given this to you. 191 minus 77. What do we get? 191 minus 77. Can somebody do that, please? 191 minus 77. Use the entire chat box, please. Don't DM. Use the chat box. It's 114 and 116. Thank you, Bilal. So 114 and 116. That's what Bilal said. Now, total number of electron shells. First of all, you could figure out the total number of electron shells by filling out the electronic configuration, by writing the electronic configuration. But the easier way to do that is to check out which period rhodium is in. If you figure out which period it is in, the period corroborates to the period correlates to what? What does the period correlate to? It correlates to the number of outermost electron shells, or the total number of shells, sorry. So if you have rhodium right here in this particular period, now if you figure out the period, you would know the total number of shells. So that's period 1, because the horizontal rows are periods and it tells us the number of shells. So if this is period 1, aka row 1, that's going to tell you that they will have 1 shell. This period would have 2 shells, this would have 3 shells, this would have 4 shells, and the period in which rhodium is in, that has 5 shells. So rhodium has 5 shells. Easy. Next, 5 electron shells. Moving on. Total number of shells. Table 1.2 shows the relative abundance. What is meant by relative isotopic mass? We covered that in today's lecture. It is the mass of an atom, of an isotope, relative or compared to 1/12 of the mass of carbon 12 atom. And you could even say carbon 12 isotope, where carbon is exactly 12 units. You could add this, where carbon is exactly 12 units. That's it. Next. Finished. It's a simple definition. We covered that in today's class and we understood it in the morning. Figure 2.1 shows, figure 2.1 calculate the relative atomic mass for iridium in the alloy. So just for iridium, how do you calculate the relative atomic mass? It's the weighted average mass of the naturally occurring isotope. So you take the isotopic mass and multiply it by the abundances. That's it. So take the isotopic mass. Why am I not taking rhodium? Because it just wants the air of iridium. So I'm not going to take rhodium, obviously. So it's what? 190.96 multiplied by the abundance, which is 15.18. Plus 192.96 multiplied by the abundance, which is 34.82, divided by the total abundance, which in this case is 50. You can just add these two together. I know this is 50 and this is in the form of percentage, so these two combined would be 50. What do we get? Camel Ray. What are we getting, everybody? Yes, what do we get? 192 or 92? 192, sorry. 192.35, because you just need to write it to correct to 2 decimal place. So it's 192.35. That's it. It has no units. Relative atomic mass has no units. Isotopic mass, you could write the unit AMU with it, but atomic mass doesn't. Next, figure 3.1. So how many marks did we get? 2 and 4. And then 4 plus 3, that's 7, 8, 9, 10. We got 10 marks. Literally 10 out of 10. Just from one chapter. We got 10 marks from one chapter. Easy stuff. Question number 2. Figure 3.1 shows a sketch of some of the ionization energy of silicon. Whenever you talk about ionization energy, go to the periodic table and write which group silicon is. So I'm going to go to my periodic table and I'm going to check out that silicon is in group 14, right? Or group 4. Oops, my bad. Group 14 or group 4. Where did we go? What the hell? Let's go back up for some reason. Okay, it's in group 14 or group 4. Group 14 or group 4, right? So it has 4 electrons in its outermost shell. Now, it says complete the graph in figure 3.1 to show the 3rd to 6th ionization energy of silicon. You know that the ionization energy generally increases, right? So there's a general increase because electron is being removed from a more positively charged ion, and the number of electrons are fewer compared to the number of protons as you start to remove electrons. So the net attraction increases. So you're going to increase, obviously increases, and then it increases in the 3rd ionization energy, the 4th ionization energy, but it was in group 4. Silicon was in group 4 or group 14, whatever you want to think about it, but it has 4 electrons in its outermost shell. Silicon has 4 electrons in its outermost shell. Now, this is the first ionization energy, the second, the third, the fourth. And then, if you move on to the fifth ionization energy, obviously, the fifth ionization energy would be, removing the electron from a shell which is closer to the nucleus. So there is going to be a big jump between the fourth ionization energy and the fifth ionization energy. So I'm going to show that big jump right now. I'm going to tell the examiner, hey, the ionization energy generally increases. I'm going to make sure that my drawing is right. It generally increases, but there's a big jump between the fourth ionization energy and the fifth ionization energy. See, I'm showing this big jump. You could even draw it like this. This is the big jump, and then this, and then this. But you don't need to draw it. तो इसको थोड़ा सा और बेहतर कर लें. Let's just make it a little better. That's between the fourth and the fifth. I'm going to show a visible increase. That's it. So generally the ionization energy increases, but there's a big jump because the fifth electron is being removed from a shell closer to the nucleus. That's it, literally. And you could even draw lines if you want, but doesn't really make a difference. Construct an equation to represent the second ionization energy of silicon. So what's the second ionization energy? Second ionization energy means you have a 2 plus gaseous ion of silicon. So how do you get a 2 plus gaseous ion? Well, you'll have to have a 1 plus first, and then you'll have to remove the electron from a 1 plus ion to get a 2 plus ion. And that is basically the second ionization. Remember, it is not important to write the number 1, but it's important to write the charge on the electron. Please don't forget to write this negative dash on the electron, because that represents its charge. Just like you're writing the charge on the ion, just like that you'll have to write the charge on the electron. So always write the charge on the electron in the form of this dash. Now, vanadium, niobium, and titanium, whatever it is, tantalum, whatever, are metals of the fifth. The shorthand electronic configuration of vanadium in the ground state is this. What is meant by ground state? Ground state, remember, we've already studied what ground state is. What is ground state? Ground state for an atom is where electrons occupy the lowest energy, levels. It's the lowest energy levels, yeah? It's actually the most energetically stable form. It's the most stable. Energetically most stable. I've written most twice. So you could either say it's the form which is energetically most stable, it's the state of the atom which is energetically most stable, or where electrons occupy the lowest energy levels. Now, show the electronic configuration of vanadium using inbox notation. So vanadium is given to me right here, and I just need to use the inbox notation. 4s2. So we know that the 4s is filled first. That's 4s2. How do I know this is the 4s and not this? Because this is just one orbital and these are 5 orbitals. So that must be the d orbital. And 3d3. So it's 1, 2, 3. Because you first of all singly fill the orbitals, and that's it. 1 mark. Deduce the total number of electrons in the p subshells of vanadium atom. So if I show you vanadium atom right here, I can't go back to the periodic table again and again. So I'll just keep on adding periodic table again and again. Where is my periodic table? My beautiful periodic table. Come back. Periodic table. Where are you? Where is my periodic table? Did it just get deleted or what? What happened to it? Where did my periodic table go? I can't find it. What the hell? I guess I'll have to re-clip it right here. For some reason it just got deleted. Okay. So go back down. I'll go back down right here and I'll add the period. So what does it want? The total number of electrons in p subshell of the vanadium. So that's my periodic table. Vanadium is what? Vanadium is right here. That's V, vanadium. So how many electrons are there in vanadium's p subshells? Well, it has the 2p6 electrons and the 3p6 electrons, and that's it. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d3, right? So it has the 2p6 electrons and the 3p6 electrons, and in total there are 12 electrons in the p subshells. So a total of 12 electrons. 12, that's it. Easy peasy lemon squeezy. सर थोड़ी स्पीड कम कर लें. मानूर, इफ़ यू वॉच द रिकॉर्डिंग, स्पीड इतनी ही रहेगी यार, मतलब दोबारा 0.5 में देख लें. It's pretty easy, मतलब there's nothing about it. We've studied everything. Okay. Pelompium was the suggested name for a new element discovered in a mineral. Pelompium was later found out to be a mixture of niobium, Nb, and tantalum, whatever. Only one naturally occurring isotope exists for each Nb and Ta. Now it says how many protons and neutrons are there. Matlab it has 41 protons, NB has 41 protons, TA has 73 protons, and what are the number of neutrons? 93 minus 41, 181 minus 73. What do you get? You get 52 here, and 181 minus 73, 108. That's it. मतलब ये तो O levels भी नहीं है ना, मतलब this is elementary school. Now, define relative isotopic mass. We've already covered this in the morning. Mass of an atom. Of what? Of an isotope. Of an isotope. Because we said that whenever you talk about the atom, you'll have to specify which isotope you're talking about. So mass of an atom of an isotope relative or compared to 1/12 of the mass of carbon 12 atom. Of carbon 12 isotope or atom, where carbon is exactly 12 units. You could add that on. A sample of polympium contains 90.9% by mass of Nb and 9.1% by mass of Ta. Calculate the theoretical relative atomic mass of polympium based on these data and table 1.1. So I've been given the abundances, which is 90.9, and then this is 9.1%. But should I take this as the isotopic mass or the isotopic mass which is already given to me? I've been given the isotopic mass, which is this and this. So don't take the mass numbers. Take the isotopic mass which is given to you correct to do 2dp. 92.91 and 180.95. Remember we discussed this. So 92.91 multiplied by the abundance, which is 90.9, plus, what does that give me? 180.95. 180.95 multiplied by 9.1 divided by the total abundance, which is 100. What do we get? Sir, why are these questions so easy? Because Yahya, you have your conceptual understanding. Literally, that's A levels for you right there. So NB and TA. What do we get, guys? 2 decimal places. So it's 100.92. Thank you. No units. No units. AR has no units. Isotopic mass you can write AMU, because AMU literally means what? It's unified atomic mass unit. It just is a short way of saying mass of 1/12 of a carbon 12 isotope. That's what AMU is, which we studied in the morning. Next question shows a sketch of ionization energy of phosphorus. Which group is phosphorus in? Which group is phosphorus in? Well, let's add our periodic table. Which group is phosphorus in? Phosphorus is right here in group 15. Or group 15, or you could also think of it as group 5, So its group 5 has 5 electrons in its outermost shell. So there's going to be, if you have 5 electrons in its outermost shell, 1, 2, 3, 4, 5, you remove this, that's the first ionization energy, the second, the third, the fourth, the fifth. But once you move on to remove the 6th electron, between the 5th ionization energy and the 6th ionization energy, there's going to be a huge jump. There's going to be a big jump. Why? Because the 6th electron is being removed from a shell closer to the nucleus. So there's going to be a general increase, 3rd, 4th, 5th. But between the 5th and the 6th, there's going to be a big jump. Why? Because the 6th electron is being removed from a shell closer to the nucleus. And see, you can show this big jump. So this was this, and then that's the big jump, and then this is this. So see, you have to visibly show to the examiner this big jump. Next, construct an equation to represent the 3rd ionization energy of phosphorus. So if 3rd ionization of energy of phosphorus is required, that means a phosphorus 3+ ion is going to form. And a 3+ ion forms from a 2+ ion. So then from a 2+, you go on to a 3+ by removing 1 mole of electrons. That's it. Next, complete graph. We've already completed it. Figure 2, relevant. What is the proton number? Proton number, check out from the periodic table. Magnesium is 12 and aluminum is 13. Number of electrons. Well, magnesium has a 2+ charge. It means it has 2 fewer electrons compared to protons. Aluminum has a 3+ charge. That means it has 3 fewer electrons compared to protons. No, Hashir, it's not necessary that it's very accurate. Just make sure that it's just even these lines that I've drawn are not that accurate, but I'm just showing a general increase. It's better that it's straight. So it's a general increase, not an exponential increase. So it's better that the trend is straight line, and then there's a big jump, and then there's a straight line. That's it. Just like you drew the graph for ionization energy. Determine the full electronic configuration of iron 3 plus. For that, remember, what did I teach you guys? I taught you guys to write the electronic configuration of iron first. Always, whenever you want to write the electronic configuration of something, of an ion, always write the electronic configuration of its atom. So iron is where? Iron is right here. What's the electronic configuration of iron? It is, I'm going to write the shorthand. So it's argon 4s2 3d1 2 3 4 5 6. Argon 4s2 3d6. Argon 4s2 3d6. I'm just combining the d first, right? The 3 with the 3's, the principal quantum numbers together. Now, what is iron 3 plus electronic configuration? Well, you first of all remove the electron from the higher principal quantum number. So the 4s loses the electrons, and then the 3d will lose the third electron. So 2 electrons goes from this, and 1 electron goes from this, giving you 5 more electrons in the d orbital, right? In the d subshell. So what is the full? It's not saying write the shorthand electronic configuration. It wants the full electronic configuration. So the full electronic configuration is what? 1s2, 2s2, 2p6, 3s2, 3p6, and then after that 3d 5, because we first of all have to write the electronic configuration of argon. So 1s2, 2s2, 2p6, 3s2, 3p6, that's argon, and then it's 3d5. Next. The elements phosphorus, sulfur, and chlorine are in period 3 of the periodic table. Table 1.1 shows some properties of phosphorus to chlorine. Okay, great stuff. Let me always add your periodic table. Always have your periodic table by your side. Whenever you solve questions in the exam, always have the periodic, tear out the last page where the periodic table is attached and put it in front of you, because you'll need it. So it's saying the first ionization energy of sulfur is not shown. Now remember the exception. If this is a period 3 for me, I know that phosphorus, the ionization energy increases across the period. Why? Because there's increase in nuclear charge, the shielding remains constant, almost remains constant, and therefore the effective nuclear charge increases and the net attraction increases, and therefore there's a stronger pull that on the outermost electron, or the outermost electron experiences a stronger pull, and therefore it requires a higher ionization energy. But remember, this was the exception between phosphorus and sulfur. That's uno exception. Why is this and between magnesium and aluminum? But I am concerned about phosphorus and sulfur. Remember, why is this an exception? Because phosphorus is 3p3. It has 3 electrons in its p orbital, or in its p subshell, right? Whereas sulfur has a paired electron in one of its 3p orbital. And so you realize that phosphorus, singly filled orbitals are more stable, first of all, and secondly, sulfur has a pair of electrons, has 2 electrons in one of its 3p orbital, due to which there is spin pair repulsion, and that is why phosphorus is going to have a higher ionization energy compared to sulfur. Remember this stuff, good stuff, and even though sulfur has a higher nuclear charge, but due to the spin pair repulsion, the ionization energy decreases, right? So it says construct an equation to represent the first ionization energy of phosphorus. First of all, let's do that. So for phosphorus, it's the first ionization energy, right? So P gas goes into P1 plus gas, and that gives me electrons. It's not necessary that you write 1, but always write the sign on the electron. And how do you define ionization energy? The first ionization energy, the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to give you 1 mole of positive gaseous ions, right? And I forgot to complete table 1.1. So complete table 1.1 to show the number of electrons in the 3p subshell and the total number of unpaired electrons. So how many number of electrons are there in the 3p subshell for phosphorus, sulfur, and chlorine? Total number of electrons in the 3p subshell for phosphorus, sulfur, and chlorine. So for phosphorus, there are 3 electrons. See, 1, 2, 3. So there are 3 electrons. It's 3p3. So 3 electrons in the p. Sulfur is 3p4. 1, 2, 3, 4. So sulfur has 4 electrons, and chlorine 1, 2, 3, 4, 5. So chlorine is 3p5. It has 5p electrons, right? So the number of electrons in the 3p subshell, it's 3. It's 3, 4, and 5. Next, the total number of unpaired electrons. For that, you'll remember, if you were to talk about unpaired electrons, you'll have to write down the electron inbox diagrams, or the electronic configuration in terms of orbitals. So phosphorus is this, it's 3p3. Sulfur is what? 3p1, 2, 3, and then 3p4. That's sulfur. And chlorine is 3p1, 2, 3, and then it is 3p5, right? So 3p4, 3p5. So chlorine has one unpaired p orbital, 3p orbital, and sulfur has two unpaired 3p orbital, and phosphorus has three unpaired 3p orbitals. So where did it go? The total number of unpaired electrons. So unpaired electrons in phosphorus are, all the three are unpaired. Here in S, two are unpaired, and in chlorine only one is unpaired. That's it. Asan hai ki mushkil? Yeah. Complete table 1.1, and now it says, okay, we've done that, we've done this, done and dusted. Three possible values of first ionization or energy of sulfur are given. Explain your choice by comparing your chosen value to those of P and Cl. It's a 4-mark question. So, phosphorus is 1060 and chlorine is 1260. How much should sulfur be? Should sulfur be more than phosphorus or less than phosphorus? Sulfur should be more than phosphorus or less than phosphorus. It's the exception. So it should be what? It should be less than phosphorus. I'll put a circle right here. And now you'll have to explain it. You'll have to explain to the examiner. Compare it to, compare sulfur to phosphorus as well as to chlorine. So I'm going to explain it. It doesn't really matter what English you write. What matters is that the concept is clearly communicated to the examiner. So my concept is clear. I'll tell the examiner that, hey, sulfur, although sulfur has S has, a higher nuclear charge versus P, it experiences spin pair repulsion due to two electrons, or due to a pair of electrons in one of its 3p orbital, due to which it has lower ionization energy versus phosphorus. I compared it to phosphorus, 2 marks, 1 mark for this, and probably 2 marks for these two things. And then I'll also compare it to chlorine. Further, chlorine has higher nuclear charge, and since shielding is constant, almost constant, it also has a higher effective nuclear charge compared to sulfur, and thus has stronger has a stronger attraction and therefore higher ionization energy. Furthermore, I'll also add one more thing. This is the complete answer, but if you want to add something else, you could also say phosphorus has singly filled. I'm also going to add the perspective of phosphorus, that it has singly filled 3p orbitals, which is more stable. That's it. So I've added all the concepts that I knew, and I just wrote it down. And you could have said that although sulfur has a higher nuclear charge versus phosphorus, this factor is outweighed. This factor is outweighed. I'm just adding English. Outweighed by it experiencing spin pair repulsion. So although sulfur has a higher nuclear charge compared to phosphorus, this factor is outweighed by it experiencing spin pair repulsion due to two electrons in one of its 3p orbitals, due to which it has a lower ionization energy versus phosphorus. Further, chlorine has a higher ionization energy, and since chlorine has a higher nuclear charge, and since Z is almost constant across the period, it also has a higher Z effective versus sulfur, and thus has stronger attraction and higher ionization energy compared to sulfur, versus sulfur. So I explained everything, with regard to this stuff right here. And P also has singly filled, which is more stable and hence has a higher ionization energy than sulfur. So this is like a distinction answer. But it doesn't matter whether you write the answer just like I am writing it, as long as you're communicating all the concepts. Give the full electronic configuration of P3 minus. Again, where is my periodic table? P3 minus, it means it has gained 3 electrons. So if this is phosphorus, make it gain 3 electrons. So it'll move 1 here, 1 here, 1 here. So it'll have the same electronic configuration as argon. So it's 1s2, 2s2, 2p6, 3s2, and 3p6. That's it. The same as argon, 1s2, 2s2, 2p6, 3s2, 3p6. Khatam, khalas. Easy or mushkil? Table 1.1 shows some properties of silicon to sulfur. The first ionization of energy of phosphorus now is not shown. Okay. Total number of electrons in the S subshell of silicon, phosphorus, and sulfur. Where's my periodic table? Where in the hell is my periodic table? It's right here. So, total number of electrons in silicon, phosphorus, and sulfur in the S subshell. So, silicon is where? Right here. Silicon is right here, phosphorus is right here, and sulfur is right here. So how many electrons does silicon, phosphorus, and sulfur have in the S subshell? It has 3s2, 2s2, and 1s2. So how many electrons? 1 in the 1s2. You don't even have to write the electronic configuration. See, 2 electrons in the 1s2, 2 electrons in the 2s2, and 2 electrons in the 3s2. And then you go on to silicon, phosphorus, and sulfur. So in total you have 6 electrons. 6 in the subshell. 6, 6, 6 for all 3. Yeah? But the P would be different. So now it's saying the total number of electrons in the P subshell. So the P subshell starts from here. So they have 2p6, 6 electrons here, and then silicon has 6 here, 7, 8. So silicon has 8 electrons because it's 2p6 and 3p2. So 2p6 and then it has 3p2. And then phosphorus is 2p6 and 3p3. And sulfur is 2p6 and 3p4. How easy is this? So silicon has 6 plus 2, 8 electrons. Phosphorus has 9, sulfur has 10 in the P. See, you have to read it carefully in the P subshells. So 8, 9, 10. That's it. Literally 2 marks for 2 seconds. 2 seconds. Complete figure 2 1.1 already done, dusted. Next, construct the equation to represent the first ionization energy of silicon. Well, first ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to give 1 mole of positive gaseous ions. Next. 3 possible values of the first ionization energy of phosphorus are given. So is it gonna be higher than silicon, lower than silicon, or equal to silicon? Let's check this out. So silicon, phosphorus, and sulfur. Which of these should I select? Let's check this out. So silicon is right here and phosphorus. So it's not an exception, you know. So the ionization energy should be higher than silicon. For phosphorus, it should be higher than silicon, and it should also be higher than sulfur. Why? Because silicon, say across the period, it's obviously getting higher, but it's higher than sulfur because sulfur and phosphorus, there's the exception here. Sulfur has a lower ionization energy because firstly spin pair repulsion, which is outweighed by the increase in nuclear charge. Yeah. So it should be higher than silicon as well as higher than sulfur. The concepts must be clear. So silicon is right here 1786 and sulfur, so it must be higher than 1786, so it should be 1060. Explain your choice including a comparison of your chosen value to those of silicon and sulfur. So why did I choose this? Because phosphorus first of all has singly filled 3p orbitals, hence more stable. Firstly. Secondly, I also know that across the period, if I were to compare it to silicon, compared to silicon, it has, compared to Si, it has higher ionization energy because across the period, it's just normal things that we write, because across the period, what happens? Across period, Z increases, shielding remains constant, almost remains constant, and the effective nuclear charge increases, and thus there is stronger attraction experienced by the phosphorus electron compared to versus the silicon electron, the outermost electron of silicon, right? Next, let's compare it to sulfur even. Let's now compare it to sulfur. So why? Because although, or not like this, I'm going to say that sulfur experiences spin pair repulsion, SPR, I'll write spin pair repulsion due to a pair of electrons in its 3p orbital. this factor outweighs the fact that outweighs, see, my English is changing, doesn't matter, but the idea is the same, outweighs the increase in nuclear, this factor outweighs the increase in nuclear charge of sulfur, hence has a lower ionization energy versus phosphorus. खत्म, मतलब और कितना आसान करके दूं? You know, we've already studied all of this. I hope you guys can recall it even. So 3 points and 3 marks. 1 mark for choosing the correct this, and then 3 marks here. कितना आसान है? Next, I think this is repetition. Explain your choice. Okay, in this case now we have to select sulfur's ionization energy. So number of electrons in the 3p subshell. Now it's just talking about the 3p subshell. So in the 3p subshell, for what? For what, sorry? What do you want? You want for phosphorus, sulfur and chlorine. So in the 3p, phosphorus, sulfur and chlorine. So phosphorus has 3 electrons in the 3p, 1, 2, 3. Sulfur is 1, 2, 3, 4. And chlorine is 1, 2, 3, 4, 5. So 3, 4 and 5. It's 3, 4 and 5. Whoosh, that's how many electrons are there in the P. The total number of unpaired electrons. So if I want to check out the unpaired electrons, see, before, neon, and if I just look at phosphorus, sulfur and chlorine, I know that these are all paired, this is all paired. The only unpaired electrons would be right here in the 3p, right? So let's check this out. So phosphorus is 3p3, sulfur is 3p4, and chlorine is 3p5. So if I were to draw the electron inbox diagram, you have 3 unpaired electrons in phosphorus, then you have 2 unpaired electrons in sulfur, and then in chlorine you have 3, 4, 5. You only have 1 unpaired electron. So in phosphorus there are 3, in sulfur there are 2, and then in chlorine there is 1. So 3, 2, 1. 3, 2, 1. Asan, mushkil. Easy peasy lemon squeezy, or no? It's difficult. Complete the table already done. Construct an equation to represent the first ionization energy of phosphorus. P gas goes into P plus, and then that gives me electron. The possible first ionization energy of sulfur is given. Explain your choice by comparing the chosen. Oh, I think this is repetition. Is it not? I think this is repetition. Full electronic configuration of P3 minus. P3 minus means you go from this to 1 more electron, 1 more electron, 1 more electron. So the electronic configuration should be the same as argon, which is 1s2. Argon has 18 electrons, right? So 1s2, 2s2, 2p6, 3s2, and 3p6. That's it. Explain the choice. So what should sulfur's ionization energy be? Should it be more than phosphorus, or should it be less than phosphorus? Obviously it's less than chlorine, but should it be more or less? Obviously it should be less. I think this is repetition. We already did this. So it's 1,000. Why should it be lower than phosphorus? Because sulfur, although I'm going to write it in another way, although S has a higher nuclear charge versus phosphorus, this factor, or it has, although it has a higher nuclear charge, due to a pair of electrons, because sulfur is 3p4, right? So one of its orbital has, pair of electrons. So because of a pair of electrons in one of the 3p orbital, there is spin pair repulsion, which outweighs, although it has, let me fix the English for it, although sulfur has a higher nuclear charge than phosphorus, this factor is outweighed. This should be the English. This factor is outweighed due to a pair of electrons in one of the 3p, and therefore their spin pair repulsion and ionization energy is lower for sulfur. Firstly. Second of all, I'll say that chlorine has a higher Z, and also has a higher Z effective. So stronger attraction. So stronger attraction versus sulfur. Therefore, higher ionization energy versus sulfur. That's it. हाय थक गया हूँ यार मैं तो. So that's how you could get your marks. Easy peasy lemon squeezing. Next. Tellurium is an element in group 16, the most common isotope after da da da. Its electronic configuration is also given to us. Complete table 1.1. So tellurium. Let's add our periodic table. Tellurium, he's also told us it's in group 16. So I go to group 16. Tellurium is right here. It has 52 protons. So how many protons does tellurium have? It has 52 protons. So the number of nucleon, the nucleon number is the total number of protons and neutrons. That's 130. The number of neutrons, 130 minus 52. What do we get? 78. And number of electrons for the atom, the number of protons and electrons are equal. 52. Khatam. Khalas. Identify the subshell in an atom of Te that contains, which subshell would contain electrons in the lowest energy level? Well, the 1s subshell, then it's the 2s, then it's the 2p and so on. So which of these would have the lowest, would have electrons in the lowest energy level? In the 1s. Construct the equation for the first ionization energy of Te. So you have gaseous atoms and you remove 1 mole of electrons from 1 mole of gaseous atoms to give 1 mole of gaseous positive ions. Khatam. Next, the radius of Te ions decreases after successive ionization. Oh, this is a good question. I like this. I like this question. The radius of Te ions decreases after each successive ionization. I couldn't care less because we haven't talked about the radius for now. State 2 factors responsible for the increase in the first 6 ionization energies of Te. What are the factors? The factors are increase in nuclear charge. No, it's the same Te. You're just removing electrons. So you could say, sir, one of the factors that we remember that the ratio of protons to electrons increases. Because since you start removing electrons, there are more protons compared to electrons. Therefore, there is stronger attraction. Stronger force of attraction, and therefore the ionization energy increases. But that's just one point. And this question is specific. This was just a general point where I said you are removing electron from a more positively charged ion, So this is just one factor. But I wouldn't write this factor if I were you. I would specifically look into Te. So if you were to specifically look into Te, and in these questions, always write the electronic configuration for yourself. So what's the electronic configuration of Te? He's given it to you, but you could also write it on your own. It's what? It's krypton, 5s2, 4d10, and 5p1, 2, 3, 4. So it's krypton, 4d10, 5s2, and 5p4, right? 5p4. And he's also given it to me right here. See, krypton, 4d10, 5s2, 5p4. First of all, the 5s is filled before the 4d. Remember that. 5s filled before the 4d. So, krypton, 4d10, 5s2, 5p. I'll write it for you. Think in terms of electronic configuration. 5p1, 2, 3, 4. Think about it. Soche. Correlate it with the exceptions that you've learned. Think of removing this one electron, then think of removing the other electron, and think whether you've seen something like this. फिर मैं आपको लिखता हूँ. फिर मैं आपको आंसर देता हूँ इसका. Did you guys think? If you did think, now let's see whether your thought process is correct. See, think about it. I removed the first electron. Okay. I removed the first electron. Now I just have to remove 3 more electrons. Have you seen something like this? Have you seen something where you are removing 1 electron which is paired and then 1 electron from a singly filled subshell? Have you seen something like this? Yes, we have between the P and the S. Remember, S had a lower ionization energy because the electron was removed. One of the electron was in one of the, 2 electrons in the 3p orbital were paired. So therefore there was spin pair repulsion. But phosphorus was singly filled. Can you not see this phenomenon right here? So between the first and the second ionization energy, my question to you guys is, which one would be easier to remove, the first electron or the second electron? Obviously the first electron is easier to remove, and you'll see a slight, increase in ionization energy, so you could say, hey, there's increase in ionization energy between the first ionization energy and the second ionization energy. And what's the reason for it? Due to spin pair repulsion in first ionization energy, for first ionization energy, not in, for first of ionization energy. That's one of the factors. Done. Then I'm going to remove 3 more electrons, right? Because I have to remove total of 6 electrons. Okay, remove this, remove this, remove this. All of this has now been removed. Now I'm going to start to remove electrons from the 5s, right? Now I'm going to start to remove electrons from the 5s. Would there be a larger, not a big jump, but would there be a slightly larger jump between the 4th ionization energy and the 5th ionization energy? I've seen something like this as well. Such a beautiful question. I've seen something like this as well between magnesium and aluminum. Remember, magnesium was what? 3s2 or 2s2, whatever it was. It was s2, and aluminum was p1. So remember, the p electron was already at a higher energy level, so removing it was easy. And you also realize that the p electron faced additional shielding, but magnesium is facing shielding. This 5s electrons are, shielded only by the 3d, but the 5p electrons were shielded by the 5s2 and the 4d10. So you'll realize that the ionization energy increases because the 5p electrons were experienced greater shielding compared to the 5s electrons. So you could also identify this, that there's gonna be an increase in ionization energy. Which two ionization energy? Between the 4th ionization energy and the 5th ionization. So he basically combined the two factors that you learn as exceptions. And what is the reason for it? Due to decreased shielding in the 4th ionization energy, for the 4th ionization energy. Or sorry, no, due to increased shielding for the 4th ionization energy and decreased shielding for the 5th ionization energy. Done? Due to decreased shielding for the 5th ionization energy. Because realize that when you are going to remove the 5th electron, it's being removed from the s subshell and it's only being shielded by the 4d electrons. But when you were removing the 5p electrons, it's experiencing shielding by the 5s and the 4d. So he's combined the exception of magnesium and aluminum as well as the exception of phosphorus and sulfur. How beautiful. So it was better to write these two statements rather than just writing this statement. But you could have written any of these 3 statements, any 2 out of these. Now, sketch a graph in 5.1 to show the first 7 ionization energies of Te. It's a very beautiful question. Sorry, Te, why am I putting a dash? Now, first 7 ionization energy. Te was 4d10, 5s2, and 5p4. So I removed the first electron, which was already paired, so spin pair repulsion, and obviously that's the ionization energy right here, right? Then I removed the second electron. There's no spin pair repulsion, so it requires a higher ionization energy. Then I removed the third electron. Obviously, removed the third electron. Good stuff. And then I'm going to remove the 4th electron. Okay, good stuff. Remove the 4th electron. And then I'm going to remove the 5th electron. Now, please understand that when I'm removing the 5th electron, where am I removing it from? There's not going to be a big jump. Because the principal quantum number is the same. But you'll also realize that, hey, removing the 5th electron is basically experiencing decreased shielding compared to the 4 electrons that I removed. The 4th electron is going to experience shielding from both these subshells, and the 5th electron is only going to experience shielding from 4d10, right? So realize that there's not going to be a big jump because the principal quantum number is the same, but there's going to be a slightly higher increase. So between the 4th and the 5th ionization energy, there's going to be a slightly higher increase. Not a big jump, but a slightly higher increase in ionization energy. So I've removed the 4 electrons, and then I have removed the 2 more electrons of in the 5s. So 4 electrons in the 5p, then 1 electron. Let me just draw it a little higher so the examiner knows that I know for a fact that there's going to be a slight increase, right, between the 4th and the 5th. And then the 6th ionization energy is again from the 5s, so that's like just a slight increase. And then the 7th electron is being removed. Then the 7th electron is being removed from a shell which is closer to the nucleus, right? So now the principal quantum number is changing. So the gap, let me draw it again. The gap between these two should not be higher than the gap between the 6th and the 7th, because the principal quantum number is changing right now. So the 6th and 7th ionization energy should be way higher, should be right here, should be way higher. These two should be higher, and then the 6th and 7th should be way higher. So let me draw it a little better. So it's the first, the second, the third, the 4th, but between the 4th and 5th, a slightly higher ionization energy, and then the 6th, and then between the 6th and the 7th, the highest jump, because the principal quantum number is changing. So this is how it should look. It should look like this. It should look like this. This additional shielding is no longer there, and then that's just like, just like this, and then this is the highest jump, because the principal quantum number, the 7th electron is being removed from a shell, from a principal quantum number shell, which is closer to the nucleus. This higher jump is due to what? This jump it's not a jump per se. This slightly higher increase is because the 5s only experiences shielding from the 4D, but the 5p was experiencing shielding from this. So the 5s experiences decreased shielding. That's the idea. Any questions? Maze ka sawal tha. This was one of the most technical questions asked by the examiner. Which year is this in? 2023. It's a technical question. A lot of students might think that they got it right, but see, there were so many technicalities that you had to factor in. समझ आ रही है कि नहीं? वैसे हैं? समझ आ रही है कि नहीं? दिमाग फ्राई हो रहा है कि नहीं? Define unified atomic mass unit. What is unified atomic mass unit? It is the mass. Remember, it was just a short way of saying the mass of 1/12 of a carbon-12 atom. So mass of 1/12 of a carbon-12 atom, where carbon is exactly 12 units. Carbon is exactly 12 units. Define the relative atomic mass in terms of unified. So what was relative atomic mass? It was the weighted average mass, or the weighted mean of naturally occurring isotopes, relative to the mass of 1/12 of a carbon-12 atom. So in this case, I'm going to say relative to unified atomic mass unit, because unified atomic mass unit is effectively what? Unified atomic mass unit is effectively what? The mass of 1/12 of a carbon-12 atom, where carbon is exactly 12 units. So instead of saying it is the weighted average mass of the naturally occurring isotopes of an element relative to the mass of 1/12 of a carbon-12 atom, instead of saying that, you just substitute it by saying unified atomic mass unit of an element, obviously. Khatam. Calculate the AR of copper in this sample using the data in figure 1.1. So how do you calculate the AR? Take the relative isotopic mass and multiply it by their abundances. So the relative isotopic mass is what? 62.930 multiplied by the abundance plus 64.928 multiplied by the abundance divided by the total abundance, which in this case is, because it's in form of percentage, you could use the calculator, even it's 100. What do we get, guys? Somebody help me out. What do we get? 63.564? 564 or 546? 546. Okay, thanks. And because see, I'm not gonna write it as 63.546, although I should write it till 63.546 because the relative isotopic mass is also to 3 decimal points. But remember, always write your answer correct to the least decimal places or the least significant figures given in the question. So here you're given 5 significant figures, here you're given 4 significant figures. So I'm going to select 4 because it has to do with accuracy, and I'll teach you that later on. So I'm going to select the 4 significant figures. So instead of writing 63.546, I write 63.55. I just round it off. Because the least accurate data in the question is till 2 dp. So always take the least accurate data in writing your final answer. Identify the ion with the abundance of 23% in the sample. So you're saying pure copper is here. See, this is 31.5, this is 32.5, and this is 63 and 65. This means that if I divide 63 by 2, what does that give me? That gives me 31.5. If I divide 65 by 2, that gives me 32.5. So which ion? This is copper 1 plus. This is also copper 1 plus because the mass spectrometer deals with ions. So it's copper 1 plus having a mass of 63. This is copper 1 mass plus having the mass of 65. And how do I know what this mass is? Well, this is mass to charge ratio, which means that now instead of having copper 1 plus, you now have copper 2 plus having a mass of 63. Here you have copper 2 plus having a mass of 65. How do we know that? We just discovered that today in today's class, and we realized that if I take copper 63 and I just select 1 plus as its charge, it's going to give me, the mass to charge ratio is going to be 63. But if I take 63 and I take 2 plus as the charge, the mass to charge ratio is going to be 31.5. That's why you're seeing a peak at 31.5 right here. So the mass, identify the ion. Which ion is this? It's copper 2 plus ion with a mass number of 63. That's what it is. This 60, it doesn't mean that this now is 31.5. No, it's just because of the charge that you see a peak at 31.5. It still has a mass of 63 because these are the naturally occurring isotopes. The reason why you're getting this is because, you were able to remove one further electron, and that's why you got copper 2 plus right here. State the full electronic configuration of copper 2 plus. First of all, write the electronic configuration of copper. What's the electronic configuration of copper? Copper's electronic configuration. Remember copper was one of our exceptions. The periodic table error. So it's what? It's argon. Copper is what? Argon. And then it's 4s2 3d9. But remember, there's no such thing as 4s2 3d9. There's no such thing as 4s2 and 3d9. The ground state is not this. Remember, if one electron can fully fill the d subshell, or if one electron can singly fill all the d subshells, then you'll have to, move one electron from the 4s to the 3d. So it's not 4s2 3d9, it's actually 4s1 3d10, right? And we've studied this. That was the exception. Remember, copper and chromium, they were the two exceptions. So even the periodic table gives you the wrong electronic configuration. You'll have to fix it by yourself. So it's argon 3d10 4s1. That's the electronic configuration. So argon 3d10 4s1. Now you just need to remove 2 electrons. So one will go from here and one will go from here. So you're going to be left with argon 3d9. And what's the electronic configuration of argon? 1s2, 2s2, 2p6, 3s2, 3p6. That's argon because it wants the full electronic configuration, not the shorthand. And then you have 3d9. And some students also tend to write 4 as 0. That's up to them. If you want to write 4 as 0, you can write it. If you don't want to write 4 as 0, that's fine. Not necessary. 4 as 0 is not important to write. The Pauling electronegativity values of the elements blah 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 are used to predict chemical properties. We have not studied electronegativity yet. We'll study it in tomorrow's class. But it says write the equation which represents the first ionization energy of hydrogen. Well, hydrogen gaseous atoms gives me hydrogen. Positive ions by removal of 1 mole of electrons. Always write the charge on the electrons. Explain why there is no information given in table 1.1 about the second ionization energy of hydrogen. Why? Because hydrogen only has 1 electron in its one electron in totality. It cannot undergo, a second ionization energy because hydrogen only has 1 electron. So how in the hell, examiner? How in the hell would it have second ionization energy? And that's the correct answer for it. Please just don't write how in the hell, but fine. Hydrogen only has 1 electron. A level is very conceptual. As long as your concepts are crisp and clear, even if it's not written in the marking scheme, you'll get full marks for it because it's very diverse, it's very advanced. So because hydrogen only has one electron, the examiner wants to check out whether you know the concept. You just have to convey it to him. So you could say hydrogen 1 plus has no electron. You could say it cannot undergo a second ionization energy because hydrogen only has one electron, and whatever. So it's up to you, but you have to communicate the idea properly. Give the full electronic configuration of S2 plus. Full electronic configuration of S2 plus. Where's my periodic table? S2 plus, where is S2 plus? S is right here. So 2 plus means that it loses one electron and it loses another electron. So it goes right here to silicon's electronic configuration. But first of all, let's just write the electronic configuration of sulfur. Always write the electronic configuration of sulfur, of positive ions. So it's 1s2, 2s2, 2p6, 3s2, right here, see? 1s2, 2s2, 2p6, 3s2, and then it's 3p1, 2, 3, 4. So it's 3p4. That's the electronic configuration of sulfur. S2 plus would mean you're removing 2 electrons. So now you don't have 3p4. Now it's going to be 3p2. 3p2. That's it. That's for sulfur 2 plus. So it's 1s2, 2s2, 2p6, 3s2, and 3p2. That's it. Next. Agla sawal. Gallium has 2 isotopes. Gallium 69, 71. Great stuff. Complete table 1.1 to show the protons. Go to the periodic table, check out how many protons gallium has. Where's my periodic table? Gallium is right here. How many protons does it have? It has 31 protons. So using this, it has 31 protons. Oh, my bad. It has 31 protons. It has 31 protons. What are the number of neutrons? Well, 69 minus 31 and 71 minus 31. That's 38. And 71 minus 31, that's 40. And how many electrons are there? They're both atoms, so the number of protons and electrons are equal. 31, 31. Khatam. Define relative isotopic mass. Again, it is the weighted average mass. It is the weighted mean or the weighted average mass of naturally occurring isotopes of an element relative to 1/12 of the mass of carbon 12 atom, or the mass of carbon 12 atom, where carbon is exactly 12 units. Where carbon is exactly 12 units. Done and dusted. Next. The relative atomic mass of gallium is 69.723. The relative isotopic masses are 69.926 and 70.925. Calculate the abundance. See, we literally in the morning we did the same question with chlorine. Remember calculation of abundance? So I have 68.926. I don't know the abundance. I'll call it X. And I know that this is 70.925. The abundance is going to be what? 100 minus X, because if one has the abundance of X, the other will be 100 minus X. It's given in the form of percentages. So it says assume that it only contains 2 isotopes. Yes, I could have only solved this if this assumption was true. Calculate the answer to 4 significant figures. It wants the percentage abundance of gallium 69. So it basically wants the abundance of this stuff right here. It wants you to give me the answer of X. So how do you calculate the AR? 68.925 multiplied by X plus 70.925 multiplied by 100 minus X divided by the total abundance, which is 100, equal to the relative atomic mass, which in this case is given. It's 69.723. And you could use your calculator to get the answer for X. You could either solve this arithmetically or use the calculator to get the answer for X. How do you use the calculator? See, I'm gonna type 68.926, then I'll use the word alpha, and then I'll click on this bracket right here which says X. So alpha X, that gives me X. And before that, I'll also use these double fraction. I'll add the fraction so it's easier for me to calculate it. I'll add the fraction right here. If you guys can see, I've added fraction. Now I'm going to complete the numerator and then I'll go on to the denominator. So is this, always use brackets. So it's like 68.926 multiplied by X plus 70.925 multiplied by 100 minus alpha X, and then it's divided by 100, and you equal it to, you press alpha calc, that will give you the equal sign, and it's equal to 69.723, and then you press shift calculate. What do we get? We get 60.13. We get 60.13, correct? 60.1300%. So it's 60.13%. That's 4 significant figures. This is 1, 2, 3, 4. Done. Agla sawal. Explain why potassium also has 2 stable isotopes. Both isotopes have the same chemical properties. Explain why both isotopes of potassium have same chemical properties. Because they have the same electronic configuration. Or you could say same number of outermost. See, if you say they have the same electronic configuration, that means that they have the same number of outermost electrons. Outermost electrons, because it's the outermost electrons which are involved in bonding. But if they have the same electronic configuration, that means it has the same number of outermost. State the full electronic configuration of potassium. Where's my periodic table? See, potassium is right here. So what's the electronic configuration? It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. That's it. So it's 1s2, 2s2, 2p6, 3s2, 3p6, and then it's 4s1. Now it says the first, second, and third ionization energy of potassium is 416, 3070, and 4600 respectively. Use this information to explain why potassium is in group 1. Now, how would you use this information to explain why potassium is in group 1? Because you'll realize that it only has 1 electron in its outermost shell, and that is indicated by this jump right here. So there's a big jump. There's a big jump between the first ionization energy and second ionization energy, indicating, what does that indicate? Indicating that the second electron is removed from a shell closer to the nucleus. From a shell closer to the nucleus. And therefore the outermost shell would contain, outermost shell contains 1 electron. That's it. Big jump. Big jump helps me, figure out the outermost electrons. Hi. Question 15. Complete table 1.1 to show the total number of protons, electrons in the ions, in the molecular ions. So you'll individually sum the protons. So nitrogen has 7 protons, hydrogen has 1 proton, and there are 4 hydrogens. So times it by 4. 7 plus 4, that gives me 11. Carbon has 6 protons, oxygen has 8 protons. It's given in the periodic table. And you have 3 atoms of oxygen. So times it by 3. 6 plus 24, that gives me 30. Phosphorus has 15 protons given in the periodic table. Oxygen is 8, times it by 4 because you have 4 oxygen atoms. So 8 times 4, that's 32. 8 times 4, that's 32. And plus 15, that's 47. Yes? Now, total number of electrons. Well, this has a 1 plus charge. That means it has 1 fewer electron compared to proton. This is 2 minus. That means it has 2 more electrons compared to protons. And this is 3 minus, which means it has 3 more electrons compared to protons. I'm tired. वैसे आसान सवाल थे कि मुश्किल सवाल थे? It's so repetitive. मैं थक गया हूँ. I'm tired. बस मेरी बस हो गई है. आसान है, मुश्किल था. सर बस अब कल पढ़ेंगे. Okay, Manu. But was this easy or was this difficult, guys?